So what I'm going to talk to you about this morning is called From Java Code to Java Heap. And it's a presentation that hopefully will apply to anybody that either writes Java code or manages or administers applications written in Java. And what it will explain is effectively how much memory is used when you write Java code and run it to allocate objects, and how to go about profiling and analyzing a deployed application to find out where the memory is being used and how to optimize it for small memory footprints. Now, if you've been to any of the other talks from the IBM team this week, you'll have seen this slide. It's our standard legal disclaimer that effectively says, do not trust this man. Anything he says may be a lie, so don't hold it against IBM. So this is me. I've been working for IBM in IBM's Java Technology Center in the UK for 12 years now. It becomes 13 years in 3 months, I think. 3 weeks. In that time, I spent most of my time working with clients to optimize and successfully deploy applications. I also do our work in what we call consumability and serviceability, but it's kind of how to use the product, how to understand it, how to debug, diagnose problems, and so on. And I now do a little bit of work on our Java in the Cloud platform. So my background is around looking at applications, trying to optimize them for performance and to understand what they do. At the bottom are my contact details, both my email address, my profile on LinkedIn, and my SlideShare account, which is where all of the slides are going. So every presentation I do, I publish on SlideShare now, so they'll be there available for download afterwards. So the goals of this talk is to introduce you to the anatomy of a Java object, the amount of memory that's used when you do use the new operator to create a Java object. From that, we'll go and look at from simple objects through to the Java collections, so the Java util collections like array lists, hash maps, hash tables, and so on. We'll talk through the different ones, talk about the memory usage of them, the access speeds, to help you decide which is the right collection to use. We'll then look at some problems with the collections as they are today, and then we'll show you how to do some analysis and to work out how to better apply memory usage inside your application. So the agenda is to first talk about memory management for a Java application. So it's not a lesson in garbage collection. It's just how memory is laid out and how it's used when you start a Java application. We'll then talk through the anatomy of a Java object. So when you create an object, what memory is allocated. And we'll talk about those Java collections, and then I'll show you how we analyze applications internally inside IBM and some improvements that we did as a result of doing some analysis. So, memory management. When you start your Java process, so you call Java on the command line, or you run an application server or a Java product, the first thing that happens is the operating system creates a process for you. And it does exactly the same thing whether you're running C or Java or COBOL or Fortran, because actually most JVMs are just a C process. Most JVMs are actually written in C, and then a mix of assembler and a few other things thrown in. So what you get is a standard operating system process. And the maximum amount of memory that process can use depends on the architecture. If you're using 32-bit, that Java process can't use more than 4 gigabytes worth of memory. No matter how much memory you've got in your box, how much physical RAM you buy, it won't use more than 4 gigabytes. Now, if you move to 64-bit, that explodes. It goes from 4 gigabytes to, I think it's 16 exabytes, which is just massive. But if you're running 32-bit, you've got a limitation at 4 gigabytes. Now, of that, some of it is used for the operating system itself and the C language runtime, which allows the JVM to run. So some of that 4 gigabytes is reserved from the operating system. So if we represent that, and this isn't a specific operating system, it's just an idea of what the memory is used for. So say of that 4 gigabytes, you've actually got 3 gigabytes for the Java process, the Java bit of it to run. Now, in the same way that the operating system needs to use some of that memory in order to run a C process, some of that memory is used by the JVM itself, so the Java runtime. So we now have a little bit less than 3 gigabytes, maybe 2.8 in which to run our application. Now, of that 2.8 gigabytes, some of that's used for the Java heap. So when you create your Java application, you use the -xmx option to set the maximum heap size. That gets allocated. And what we've got is a little bit left over. And that little bit left over is actually used by the JVM to do stuff on behalf of Java code. So that section in there is used for things like sockets. If you create a socket or you create a thread, some OS level resources are allocated, and that goes into that middle bit. Now, we usually refer to that as the native heap, and we add in the allocation for the JVM itself as the native heap. So it becomes one big chunk that's referred to as the native heap. So of this 4 gigabytes, some's going to be used by the operating system, and that's usually a fixed size. And then you've got maybe 3 gigabytes left, which is used for both the native heap and the Java heap. And either of them can have an out-of-memory error. So if you run out of Java heap, you'll get an out-of-memory error. If you run out of native heap, you'll get an out-of-memory error. And the way you size the native heap is just by making, or you make the native heap bigger by making the Java heap smaller. That dividing line in the middle, where are we? The dividing line in the middle is specified by the -xmx setting for the maximum heap size. So as a quick guide of some of what's on the native heap, here's an example of a thread object. So you've created a new thread using new Java lang thread. And what's happened is we've allocated a thread object on the Java heap, and every thread object has a runnable and it's part of a thread group. So you've got some Java objects on the left. But on the right-hand side, on the native heap, we actually have to create an OS level thread. And that OS level thread is going to have a stack, and that stack's used for running functions and methods. And you're also going to have a Java stack with your Java operands, the things you've passed from your one method to another stored on it. And that's in the native heap as well. So when you allocate stuff on the Java heap using the new operator, sometimes you get things on both sides. Now, the anatomy of a Java object. Let's start talking about Java code, which is where we really work. So when you create an integer, right, you take an int value and you put it into a new integer object. That integer object's bigger than the int value that it contains. So the question is, how much bigger do you think the integer object is than the int value that we've stuck inside it? Who thinks they're the same size? Anyone? Okay. Who thinks the object is 1.5 times the size of the int value? So only 50% bigger. Anyone? Okay, 1. Who thinks it's twice the size? Okay, that's probably about a quarter of you. And who thinks it's 3 times the size? Okay, so either people know the answer here, or some people don't like putting their hands up, because the answer is actually 4 times the size. So there's a significant growth when you take that int and you wrap it into an integer object. So what do we actually use that extra memory for, that 4 times multiplier? So the first bit of it is, when you created your integer object, we have to know that this object is an integer. And we do that by having a pointer to its class type. So we store an identifier that says this is an integer. The next thing we do is we have a series of flags. The flags tell us whether it's an array, it stores the hash code, it stores a few other things. So we have another bit of data that's flags for the object and tells us about its state. Now you can synchronize on any object. And in order to be able to synchronize, so do synchronize in your code, in order to do that, we need to be able to have an indicator that it's synchronized or it's not and who owns it. So we add more data for that. And then we add our integer value, which in this case is 10. So here we've got the 4-to-1 multiplier of, we put an int in, but we had an extra 3 other bits of data that we had to store that makes it a Java object. Now, if you're using arrays, it's actually slightly more. We again have to have our type, so this tells us it's an array of int. We then have our flags again. We have our ability to synchronize on it. Then we have the size that says how big this array is. And then we have our integer object value of 10. So for arrays, there's more header data for your object. So there's a 5-to-1 for arrays and 4-to-1 for objects. And additionally, if you're using compressed references, compressed oops, we sometimes put padding around these objects. but that's not probably all that important. So that was 32-bit. Now, if we move to 64-bit, what happens? So the difference between 32 and 64-bit really is the amount of data that you use to reference one bit of memory to another bit. So this means that when we have that class pointer that describes the type of the object, whereas for 32-bit they were each 32 bits wide, for 64-bit they're each 64 bits wide. So the ratio of your int to the size of the object gets significantly bigger at 64-bit. And this means if you take an application that runs on 32-bit and you move it to 64-bit, it's going to use significantly more memory out of the box with no changes. So we've got this picture for Java objects, and again for Java arrays we had 4 bits of information that told you about the type of array. They were 32 bits, and for 64 bits they now become 64. So you get a significant growth in memory. Now that gives you a ratio of 9:1, which is really painful. So here's the table of the sizes of each of the data types. So an int there was 32 bits. And you can see what it is for each of them, but the important bit is the row at the bottom, objects. And this is the reference from one type of object to another. Here it's 32 for 32 bits and 64 for 64 bits, but the asterisk is depending on whether or not you're using compressed oops or compressed references. So does anyone here know what compressed references are? Okay, and does anybody use them? Okay, so where we said that there's that big growth, where we did have 32 bits for everything, and then it became 64 bits, what compressed references does is it tries to represent that data on 64-bit using 32-bit values. So it removes the big growth of where we've got lots of 32 bits to 64 bits, right? It just gets rid of it. And it does it using pointer arithmetic and offsets, which isn't that interesting, in all honesty. The fact that it removes that memory increase is. So if you're running 64-bit, basically used compressed references or compressed oops. There's very little reason not to now. So the effect of this is, without compressed oops, when you move to 64-bit, your memory usage, on average, goes up by about 70%. So if you were using a 1 gig process, it now becomes 1.7 gigabytes in size. So you use significantly more RAM when you move to 64-bit. Now, the introduction of compressed references or compressed oops solves that problem for Java objects. It doesn't solve the problem for our native heap allocations. The JVM itself, the C runtime, the threads that we create when you create a thread object on the native heap, that doesn't get improved by compressed references. So the memory usage for that still grows. So when you move to 64-bit, if you turn on compressed references, your Java heap size usage will not increase by 70%. But your off-Java heap memory usage will still increase by 60–70% or so. So you still need more RAM when you move to 64-bit, but if you use compressed references, it greatly reduces the amount. Okay, so we said for a simple object, for an int, the multiplier was 4:1 in 32 bits. Now the thing is, we don't create objects as simple as that, and the idea of Java programming and object-oriented programming is to do encapsulation and to do delegation and to basically have lots of references between objects. So if we take Java-lang string as an example, the implementation of a string object is 2 objects. You first have your Java-lang string object, and that contains a hash value, it contains a count, it contains an offset for where you are inside the string if you're manipulating it, and it has the value itself. And the value is just a pointer to another object, which is a character array. So when you create a string, you're actually creating 2 objects. So that means that we, in this case, have a size ratio of 3.75 to 1. And it would be worse if we were holding only a single character. Okay, so basically when you create an object, you're usually creating several of them, and each of them introduces its own overhead. So every single object has at least 3 words worth of extra overhead. Okay, so if we now move on to collections, so something that's a bit more complicated, but that everyone uses inside their applications. So as you go from the top of that list to the bottom, you have decreasing amounts of memory that is used by the collection in order to store your data. But you also get decreasing value. Right? So hash maps are pretty flexible. They do fast lookup, they grow, etc., etc. And they're easy to use and they perform well, but they use a lot more memory than an array list does. So if you use array lists and you can use it for your application, you'll use less memory by doing so. And most people don't actually think about the memory usage of the collection that they're using as they create it. And that's what we're gonna look at a little bit here. So the first one on the list was hash set. And hash set is just a collection that allows you to store objects with hash codes. Now, the implementation of a hash set is a hash set object that points to a hash map. So it's actually just a wrapper around a hash map. And what that wrapper does is actually give you less function. It restricts what you can do. So a hash set is bigger than a hash map, but with less function. So there's kind of an argument as to why you would want to use one in the first place. But the size of it, so when you create a hash set, even if you don't put any data into it, you just do new hash set, you'll get a hash set which is capable of holding 16 objects. So that's 16 objects which you're not storing, so you've got overhead to do nothing at this point in time. So when you create it and it's empty, it's 144 bytes in size. And that's just the wrapper around the hash map. So if we look at hash map, when you create a new hash map, what you've got is an implementation of the map interface with hashing. That means that when you try and access an object with a key, the access speed is fast. The access speed shouldn't change as the collection gets bigger. So it's a good collection to use. Again, its default size is 16. So you create it, and it's capable of putting 16 entries into it, even if you aren't putting any in. Even if you're only ever going to put 2 entries in it, it still creates it at 16 for you. Its empty size is 128 bytes. And every time you put an entry into it, what's created for you when you do a put is a new hash map entry. So you're not just putting your objects into it, there's management around those objects as well. And this is what a hash map entry looks like. So the hash map entry has 4 objects in there. One is your key and one is your value. So that's what you usually put into a hash map when you do a put. But it's also got a hash key and it's got a next pointer. So every time you put something into a hash map, it's not just your data that's being put in there. There's some wrapper around that so it uses more memory. So the effect of this is if you create a hash map to put 10,000 entries into it, but it's completely empty at this point in time, it uses 360K's worth of data. So that's a third of a megabyte to do nothing at this point in time. Okay, next, if we look at hash table. So hash table is virtually the same as hash map in terms of its memory usage. So the layout is the same. The difference is that its default size, when you create it, is 11 entries. So whereas hash map and hash set are 16, hash table is 11. Apart from that, basically it's the same, except hash tables are synchronized by default. So people often use hash tables as a safe collection because it's kind of like a hash map, but because it's synchronized, you don't have to worry about concurrency issues. The downside, of course, is it's synchronized even if you don't want it to be, which can cause you some performance problems. But again, you put a new entry into a hash table, and what you get is a new hash table entry object with a hash value, your key, your next, and your value. So again, if you had a 10,000 entry hash table, it's going to be using about a third of a megabyte. And this is just for the collection. It doesn't include any data that you're storing inside it. Next, as we go down is linked list. So a linked list is an implementation of the list interface. And linked lists are a little bit better in that their default size is 1. When you put an object into the linked list, it grows individually as you put more data into it. And its memory overhead is quite a bit lower as a result. Its empty size is only 48 bytes. When you put a new entry into it, you get a new linked list entry object in the same way you had a hash map entry object or a hash table entry object. And that's what it looks like. So because you don't have a key value pair, because there's no key, it uses a little bit less memory per entry than the hash map and the hash table. And this means that if you had a 10,000 entry linked list, it's only using 240K. So linked lists are smaller than hash tables and hash maps and hash sets. Next is array list. So an array list is just effectively a growable array. So the implementation of an array list is an array of objects. So what you've got is an array list object and the array that it manages. The default size for array list is 10. So far we've had hash set and hash map with a default size of 16, hash table with a default size of 11, and array list with a default size of 10. I would love to know where they got these from. What was the decision? I think it was kind of, maybe a bingo machine and they pressed a button. But yeah, so array lists start off with 10 for whatever reason. The empty size is much smaller because it's just a single object and an array. And one of the advantages is when you put something into an array list, you don't have to create an entry object which has memory of its own size as well. You just put it directly into the array. So this means if you had a 10,000 entry array, it only uses 40K's worth of data, whereas hash table, hash map, and so on used 360K, and linked list used 240K. So it's smaller. And there are other things which kind of behave like collections, even though they're not part of the Java util collection package. One of these is string buffers. So when you create a string buffer, it's kind of like an array list. It's a management around an array of characters. So when you create a string buffer, its default size is 16 entries. 16 characters is what you can put into it. And therefore, if you create one with nothing in it, its empty size is 72 bytes. And it's just 24 bytes worth of overhead over the data inside it. So it's really quite cheap. So there's the summary of the collections. Basically, as you go down the list, you use less memory in order to store data. But, as I said earlier on, you lose function. So you get more function in a hash map than you do in a string buffer or in an array list. So why would you use the hash collections if they're significantly larger? And what it comes down to is their speed of access. So the idea of the hash collections is as the collection grows, the amount of time it takes you to find an object in that hash collection should not change. So the access time, the update time, the modify time remains constant regardless of the size of the collection. For the non-hash type collections, you may, in the case of a linked list, have to iterate down the linked list in order to find your object. So as the collection gets bigger, your access time grows. For array lists, it can be the same. It all depends whether you're storing an index into the array list or not. So it actually may well be that using the hash collections is the right thing for you to do. But kind of if you care about memory, you want to know it's the right collection for you to be using in this case. And you want to have decided whether you're using a hash table because you want synchronization rather than a hash map. What we find by analyzing applications is that developers just seem to have habits. They don't sit down and think, which collection should I use? They just create the same collection they always do. And when you study code, you can almost work out who wrote it based on the collection types that are being used. So the next problem is empty space. I said I've kind of been highlighting that each of the collections start off with a different default size. So we had 16, we had 11, we had 10, then we had 16 again. So if we look at what happens when we create a new string buffer and put myString into it, is we've created our string buffer object, and then we have this pointer to the character array, which we said by default is 16 bytes in size, 16 characters in size. So when we put myString into it, it only uses the bottom parts of it that's required to store the string. The rest of it's wasted. So what we've got is 9 characters being stored in 16 slots. So we've got 7 that are being wasted. That's just memory that's being allocated that you're not using for anything. So that costs you an extra 112 bytes. And it actually gets worse, because string buffers are designed so that you can build strings and add more data to it. So if we look at the same thing, what we've done is we've started off with a string buffer with my string in it, and this is using 9 of our 16 characters. So if I start adding more characters into it, I'm building a bigger string. So if I put in my string of, and then I want to add text, so I want to have my string of text, what happens is as I put the extra individual characters in, once I've got as far as the X and my string buffer is full, but I still want to add an extra character into it, the string buffer grows for you so that you can put the extra data in. And it does this by doubling in size. So in order to put that extra single character into the string buffer, I had to allocate another 16 entries. So now I've got 15 spare entries, whereas previously I had, 6? So basically most collections grow and expand by doubling. The algorithm actually changes but depending on the collection, but most of them double in size. Now here it's not really that a problem. We're saying we've got 15 spare characters, and let's face it, that's not a lot of memory. But if you consider the case where what you're doing is sending large SOAP messages around, and you've gotten 7.5 meg SOAP object, and you make it 8.1 meg in size, we're now using a 16 meg string in order to store just over 8 megs worth of data. So you're wasting basically 8 meg. And this is the problem with the way it expands by doubling, is for large collections, suddenly you can go to having a huge amount of wasted memory. So the additional 16 character entries for the single character was, in this case, a waste. So if we update the summary, we've got a range of different default sizes. We've got a range of different overheads depending on function. And we've got, again, a random selection of the ways that the collections expand. In general, they work on a times 2. Linked lists are always the right size because we allocate and remove them as you allocate or add or remove objects. But yeah, in general, they double in size. And this causes that problem of, for large collections, if you just want to add a small number of extra entries, it will double in size and use twice as much memory for the collection itself. So through the whole part of this presentation, I've been talking about very small amounts of memory. Right? We said that a 10,000 entry hash map uses 360K for the hash map, and that you can get down to 40K by using an array list. So that difference is only 320K for a very large collection. And let's face it, for most SE or EE applications, you've got huge amounts of Java heap available to you. I guess, as a result of the keynotes on Sunday, there's a lot more talk about embedded, so memory will become important again. But it does sound like being able to save 1/3 of a megabyte here and there for our big caches isn't really that important. But it turns out that if you actually analyze an application, there are large numbers of collections in use in any given application, possibly a surprisingly large number. So running a simple test against the IBM Web Application Server, it happened to be version 7, and Plants by WebSphere, which is a standard demo that's shipped with it. So we ran a load test using just a simple load runner with 5 rotating users, so 5 people connected at the same time, but different user IDs being used for it and so on. And we ran that for a couple of hours, and then we took a heap dump and decided to have a look at the collections in memory. And this is what we saw. So first of all, there were 262,238 instances of hash table. So the first thing this tells me is we've definitely got at least one guy who likes hash tables. But because there's over 250,000 hash tables, the memory usage of just the hash table and the hash table entries, not the data that it's storing, is actually 26.5 megabytes. So that's 26 meg just for the hash tables themselves. Next, weak hash map. We actually have 19,500 of those, and they use 12.6 megabytes worth of memory just for the weak hash maps. Again, not the data that's stored inside them, the collection itself. Then we've got some hash maps. We've got over 10,000 of those, holding on to 2.3 megabytes. Then we've got array list. Again, almost 10,000 array lists. Because they're much, much smaller, The fact that we've got 10,000 of them means they're actually not holding on to a lot of memory. They don't use much memory themselves. We've got hash sets, not many of them, but still 1,500 using a megabyte. We've got a number of vectors, we've got linked lists, we've got tree maps. So we've got a range of different collections and a large number of instances of each, and some of them are holding on to significant amounts of memory. So in total, we've got over 300,000 different collections live on the Java heap, and they're using 42.9 megabytes worth of memory just for the bits of the collections themselves, not the data that's inside it. So that was when we were running an application with 5 parallel users, and the memory usage of the application was just over 200 meg. So it's not a big application compared to some of the things that you see being deployed running J2EE or the like. And of that 206 megabytes, the fact that 42.9 is being used for collections means that 16% of the Java heap is being used just for collection objects. So it may be we've got some scope to save some memory in there. But the question is, one, how do you find out what collections you've got and what number they are and how much memory they're using? And two, how do I find out whether I've got empty space in my collections, whether they are empty, whether they've been missized, whether someone's using the wrong collection type? How do you start digging into to find out whether you've got problems? Well, the answer is there's a tool called Memory Analyzer. Does anybody know Memory Analyzer or use it? Okay, that's good news. So Memory Analyzer is an Eclipse open source project. It's been around for 4 or 5 years now. IBM does have its own version where we take the open source and we've extended it with extra function to know about IBM products. So you can get an IBM version of this as well. But one of the things that Memory Analyzer does is it lets you take an image of your application, so a system dump or a heap dump, and it loads it in, and it knows about every single Java object that's on the Java heap, the values that are inside them, what they're being used for, the relationship between them, they do memory analysis and so on. So it's fully capable of finding all of your collections. And one of the things it will let you do is check the fill ratio. So what percentage of the collection size is actually being used to store useful data? So when you open your dump and you select collection fill ratio, it asks you whether you want to limit your search to certain types of collections, and that's just a regular expression. So I can use Java util hash table because I know IBM seems to have some hash table guys. And once I've run that, it gives me a simple breakdown of some bands of ratio and how many collections there are inside it. So that top band is objects with a fill ratio of less than or equal to 0. So basically empty hash tables. And we have 127,000 empty hash tables storing no data. So the chances here are that we've created something that just doesn't get used or doesn't get used in our existing use case. So it's great that it's told us that I've got some kind of problem, that I'm losing 10 megabytes worth of memory to 127,000 empty hash tables, but I kind of need to know who created them and what they're being used for. So can I relate it back to the code? Well, what it will do is it will let you list all of these objects, and you can choose to list them to find out what code or what other objects are referencing it, or what it references, so inbound or outbound references. So if we look at the incoming references to find out what's holding on to this hash table, we find in this case it's being used for session data. So the Plants by Webster application has asked for these hash tables in order to store some session data for its application. So it's kind of a problem in Plants by Webster for the way that we've been running that sample demo. So now I know that I've got two options. I could either say, well, let's not create the hash table until someone wants to put something into it. Why have a hash table if it's got no put to put into it? Or I could say, well, I can minimize some of the memory usage by making its default size smaller. Rather than having 11 entries for a hash table by default, if there's a good chance I'm not going to use it, I could make it a lot smaller by default. So when we went through the full analysis of all of those collections in our sample, what we found was there was a great tendency for them to be empty. Almost 50% of the hash tables were empty. When we looked at weak hash map, basically they were all empty, so they're not being used. Hash map was again high for empty. Across the board, it was kind of like 50% of the collections that were allocated and live in memory weren't being used to store any data. So they were just effectively wasting memory for us. So we then went to see how we could optimize this. Now, one of the easiest places to optimize is in the application itself, right? You know what data you're putting into it. You know whether your collection is likely to store 4 entries or 40,000 entries, and you can create them to be the right size to begin with. But we were trying to do stuff in the JDK level as well. So one of the things we looked at there was weak hash map. And weak hash map is actually quite a large object when it's empty. And one of the reasons for this is in order to do the processing of the weak hash map, to deal with the weak references in there, it has a weak reference queue. And that weak reference queue is there to process the objects that you've put into the collection. So we don't actually need that weak reference queue until there's an object that's being stored by the weak hash map. So what we did was we took our own advice and we said, well, let's allocate that weak reference queue lazily. Right, let's only create it when we've put something into our collection to begin with. So by doing that, we actually remove something like 560 bytes per weak hash map that's empty. And the effect of this is we saved 10.9 megabytes out of those empty weak hash maps just by allocating the weak reference queue lazily. So there's a number of techniques that you can apply to try and minimize your memory usage, right? The first of them is this concept of doing lazy allocation of collections, right? Rather than just creating a collection in the initialization of your object, you can wait and only create it when you want to put the first item into the collection. There's no point having a collection with nothing in it. So the moment you want to put the first item into it, that's when you should really be creating the collection, so create lazily. Secondly, you do actually have the option that if you're only going to be storing a single object, of not putting it in a collection at all. You could just store the object. The use case for that is somewhat smaller. The third is sizing collections correctly. So the fact that the default is 16 or 11 or 10 may not be right for your application. So if you're only ever going to store 4 objects inside a collection, you can create it of size 4. Right? All of the constructors let you pass a number into the constructor that says this is the size of collection that I want. Another one is to try and avoid the expansion of collections, so avoid this doubling, particularly for large collections. So you don't want to be storing 17 megs worth of string in 32 megs worth of string buffer. And finally, and this isn't one I've covered, but I'll explain now, is we said when we get to the limit of collections usage and we put one more item in it, that collection doubles in size. Now, when you then remove that extra item, so you're back down into usage that you could have done previously, that collection doesn't shrink. Right? Collections only expand. So they will always stay at the largest size that they've ever been. So this means that if you did have a one-off allocation that caused you to have a 32 meg string buffer, and you only ever use that same string buffer, it's going to stay at that size. It won't shrink again later. So if you know you have this kind of problem, one of the things you can do is create a new collection that's smaller, copy the data over and throw away the old one. So if you really do want to minimize your memory footprint, the fact that shrinkage doesn't happen is a concern, and it's something that you can implement in your own code if you want to. So with that, the summary is there's significant overhead to your data, right? When you put a bit of data that you care about into a Java object, it gets bigger. You put it into a collection, it gets bigger again. Most applications are filled up with the same type of collection because it's just what the programmer is used to using. You can be more intelligent about that. You can select the right collection. By doing so, you drop the footprint a little. Then making sure that you create them to be the same size. You make sure that they don't expand too rapidly. You worry about the fact that they may expand and not shrink, and you can replace them at smaller sizes. if you care about these things and you do it, then you will drop the footprint of your application, you will be more memory efficient, and usually smaller applications run faster. And in order to do this, the tooling that you can use is the Eclipse Memory Analyzer tool, which will do collection analysis for you and allow you to identify empty collections or collections where you only have a small number of entries for the size of them. Okay, and with that, we're through to any questions. So there is an article for this. It's on DeveloperWorks, and the slides are on SlideShare. Yes?
What's a good time to start memory analysis? I mean, when you hit performance issues or early in your development?
So the question is, when's the best time to start doing memory analysis? And the answer is the same time it is to do performance analysis. Right? A lot of people leave their performance work to late in the cycle. And suddenly you realize that in order to make my application run faster, I have to make architectural changes, and I should have done that a long time ago. And it's the same for optimizing for memory. Whether you're optimizing performance or memory, the earlier you start in the cycle, the less risk there is to your product. Yes?
Have you come across any good third-party implementations of the collection API that are more efficient in usage?
So the question is, are there any third-party implementations of collection classes which are good? The answer is yes. There's a few packages from Apache which are very good. But in general, I mean, I would like for us to go back and revisit the base collections as they are inside Java SE. They've been the same way for, well, 15 years. And the fact that the default sizes don't seem to make sense, the expansion algorithm being 2 times, is great for small collections, but the moment you're getting up to 16, 32 megs collections, a doubling really doesn't make any sense. There's no option to plug in the expansion algorithm that you want or to have it adaptive based on size. And I think those would be improvements. And I think being able to shrink as well as expand would be great as well. Yes?
When we try compressed references, we started seeing some out of native memory errors when there was plenty of native memory, and it seemed to be related to the native memory and the heap being in the same 4 gig space. Is that a common problem, or do you think that's just kind of a specific scenario?
So the question is, when using compressed references, it's possible to get a native out of memory error even though for 64-bit you have vast amounts of addressability. And the answer to that is yes, it is kind of a one-off corner case, and it's to do with how the operating system tries to get all of the memory in under the 4 gig line. I think, certainly on the IBM side, we've made enough changes now so that it automatically moves the heap to the right place to avoid it. We certainly had a couple of issues early on, and it was corner cases around where the boundary of the heap was. Yes?
A couple of your slides mentioned shallow heap and routine heap.
Yes. Okay, so shallow heap is the size of that specific object, and retained heap is the sum of that object and anything else it references. So it's the sum of the tree under it is retained, and shallow is that individual object. Okay. Yes?
If you're running multiple 32-bit JVMs on 64-bit JVMs, the 32-bit JVM supported, and the 32-bit JVM has the ability to access 4 gigabytes of memory. Will both the JVMs running both access the first 32 gigs of memory? The first 4 gigs of memory on the operating system, or will the operating system allow it to use one JVM to use 4 gigs, lower, and the next 4 gigs, the next lower?
So the question is, if you're running 32-bit on a 64-bit operating system, are you still restricted to using 4 gigs worth of memory? How's that laid out when you have multiple JVMs? So the answer is, you're still restricted to 4 gigabytes. Right? You can only use 4 gigabytes for a 32-bit process, regardless whether it's on a 64-bit machine, regardless of how much RAM you've got. Now, The layout of that in physical memory isn't just as a slab. So the operating system basically breaks up your physical memory into pages, whether they're 4K, 16K, 64K, 6 megabytes. You can now get 16 gigabyte pages, but it breaks it into pages. And some of those will be used for some applications, some of them will be used for others. There's a level of abstraction that means you can't really map chunks of physical memory to the application that uses them. But each application has visibility of its own 4 gigabytes. So yeah, everyone sees their own 4 gigabytes, and they're kind of interspersed in each other on physical memory.
So based on your last statement there, 2 JVMs that are both 32 gigs could use a combination of 8 gigs on top of it.
So yes, if you've got 8 gigabytes and you've got 2 JVMs using 4 gigabytes each, they will use 8 gigabytes total memory. Yes. Yes. So the question is, it's easy to size the collection to have the right capacity if you know what's going to happen inside your application. But if you're, I guess, a framework with someone else using your code, you don't know what you're going to use. That's where the collections are today, right? They will dynamically grow and shrink for you. Your only option there is to kind of profile the different use cases. Sometimes you do find that if our code's used in this code path, we use 4 entries. Here, we use 16, and you can try and start off with the right size based on who's calling you. That is an option, but it's painful. That's why I think there should be improvements to the collections themselves, so that it can actually be more intelligent and not just double in size, which really doesn't make a lot of sense. But yeah, it's just a problem. So the question is there any active work to change the expansion algorithms? There's been some discussion, but I don't think anyone is interested enough at the moment. I mean, it is true that you could just subclass the collection yourself, override ensure capacity, which is the expansion algorithm, and do it yourself. But at the moment, whilst we would like to do it in SE, there's no direct work being done.
So are there any improvement in the garbage collection to address these kind of issues? I understand there is a practical difficulty, but in future, is there any possibility that look at the application and then see that this kind of spilling pattern is there, the charge collection can make this and then
So the question is there any work being done in garbage collectors to try and help with this? Yes and no. I mean, there's some research projects which are going on in a couple of universities which are looking at how to do allocation profiling to work out how to allocate better. In terms of garbage collection, the simple answer really is no. Because this is all Java level, right? You have a Java object that's telling it how much memory it needs to use. So the garbage collector is too low a level to be able to influence that. Some work that has been done in garbage collection is around arraylets. So the idea is, whilst your Java application thinks that you have an array of size 16 megabytes, what the garbage collector's done for you is it's broken it down into small segments. So it's not one large object, it's a number of small objects. But that doesn't help with memory efficiency, it helps with avoiding the need to do compactions and the like because of fragmentation. Yes? Sorry. Tree map. So yes, I didn't cover tree maps, and tree maps are actually quite efficient because they grow similar to a linked list, but they don't have the same linear growth of access time. So tree maps kind of sit between linked lists and the hash collections, both in terms of lookup speed and memory footprint. Yes? So the question is, how do compressed references work? So the basic concept is for a 32-bit application, the reason why the addressability is 4 gigabytes is that a 32-bit pointer gives you numbers between 0 and 4 gigabytes. So it's the size of your pointer. Now, what they do for compressed references is rely on the fact that every object starts on an 8-byte boundary. So we don't need to be able to access everywhere in memory for a Java object, only the start of 8-byte boundaries. So that means we can actually ignore the bottom, the bottom 7 bits, right? And therefore, with a 32-bit pointer, knowing that we only care about slots on which objects can start, that gives us 32 gigs worth of addressability. So compressed references work for 64-bit heaps up to 32 gig only. To turn on compressed references, you just add, for IBM, -x compressed refs on the command line. For Oracle, I think it's -xx compressed oops. Yes?
Well, what's your advice? If we are planning to move like 32-bit applications to 64-bit OS, what's your advice? Do we need to really look at our applications?
So the question is, if I'm moving from 32-bit to 64-bit, what's the advice? Well, the first bit of advice, if you can do it, is run 32-bit on 64. Because at that point, your memory doesn't grow, and you don't have the other effect moving to 64-bit, which is your application actually runs slightly slower. Right? 64-bit applications are slower than 32-bit. So if you can stay on 32-bit on a 64-bit platform, do it. If you can't, then what you need to do is make sure you have more RAM available. So if you had a 32-bit machine that's got 12 gig of RAM in it, and you move to a 64-bit machine with 12 gig of RAM in it, you're going to have problems. So you need to make sure you've got at least 50% more RAM, probably, to be safe, double it when you move to 64-bit. Yes? So the question is there any reason not to use compressed references? And I think the fair answer to that is no. I mean, the only reason why compressed references were not enabled by default for Oracle on Hotspot, IBM did, is stability, right? It's new. As I said, IBM out of the box straight away turned it on by default, particularly under the Web Application Server for heaps up to 32 gig in size. Oracle made it optional, and I believe compressed groups became fully supported about a year ago, 18 months ago or so, but don't quote me on that. Sorry, is? So the question is, does JDK 5 support compressed references? And I think the answer is no. Certainly for IBM, our first release was Java 6 that had support for it, and I believe it's the same for Hotspot. Yes?
So, like for Mac, we can use for heap analysis. Is there any tool which can just give me a snapshot of the data memory of various? I don't want that math process memory and only the snapshot of what data that is.
So the question is, Memory Analyzer, MAT, only knows about the Java memory usage. Is there anything we'll tell you about the off-Java heap, the native memory usage? And the answer is yes. But currently you have to be running the IBM JDK. So when you get a heap dump on Hotspot, it is just an image of the Java heap. What the IBM approach is to this is to take a full OS level system dump. Right? So on Linux or AIX, it's a core file. On Windows, it's a mini dump. And you can generate those non-destructively so it doesn't crash your application. It just gives you the full image. So for that, we have access to all of the native stuff. And we've actually put a couple of things in our version of Memory Analyzer, which will access the native stuff. But we, literally 6 weeks ago, released a new tool called IDDE, Interactive Diagnostic Dump Explorer. And that does exactly that. It gives you access to both the native and the Java side and the relationship between the two. But again, it's IBM JVMs only, I'm afraid. So the question is, But that gives you both. It gives you native and Java. Is there a way to have only native? The answer is no. The dumps give you both. So yes, you pay the extra cost of writing the Java heap information as well. But core files typically compress down to 20% of their original size, so they do compress well in terms of size on disk. Yes?
Is there a difference in a virtual machine versus a physical?
The question is there a difference between running in a virtual machine or in a normal OS? And the answer is no. In terms of all of this, your virtualization layer hides that from you. The virtualization layer says that you still can only see 4 gigabytes worth of memory. It just may not be giving you 4 gigabytes under the covers. Yes?
Just a remark to hash tables and the size of hash tables is random. The performance depends on the load of the hash table. So if the hash table is full, the performance drops. So I think it's sometimes a trade-off between memory usage and performance. Performance is important. It's better to have larger hash tables because, for example, the hash table has 54 load level is 5%. So if we created a hash table with 2 objects, or the size of two objects is equal, it will automatically increase to get the load level.
So the question or the statement is that effectively collection selection is a trade-off between memory and performance. And yes, the more performant collections are the ones that cost you more memory. And you're right. Some of what I covered is a simplification. You say you use a hash collection and it's a constant access time, and that depends on your load factor and your entropy. So yeah, it's a simplification, but it's approximately right. Any other questions? Okay, then thank you for attending. As I said, the slides are on SlideShare.